Welcome students once again into the class of number theory, and this is the second video on the topic of quadratic residues. In this video we will have some more theorems, some more results, some more examples based on quadratic residues. So let us start with the first theorem, which is a little bit complicated to understand but is not difficult at all. It says that if P is a prime, then the set, in fact P is an odd prime, you can say. If P is an odd prime, then the set, this set 1, 2, 3 and so on up to P minus 1 contains exactly P minus 1 by 2 quadratic residues and P minus 1 by 2 quadratic non-residues. So this is the basic thing. That means, for an example, if you take your P to be 11 and consider this set is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. This set, according to this theorem, according to this statement, this set will contain exactly 5, half of the number of elements, exactly 5 quadratic residues modulo 11 and exactly 5 quadratic non-residues modulo 11. What these quadratic residues are, what these quadratic non-residues are, this we will find in this video after doing one or two theorems. But let us see first how to prove this theorem that the set 1, 2, 3 up to and so on P minus 1 contains exactly P minus 1 by 2 quadratic residues and exactly P minus 1 by 2 quadratic non-residues. Now this set is, for the proof I am going to start, this set is 1, 2, 3 and so on. In the halfway, on the middle, you will get P minus 1 by 2 and P plus 1 by 2. And in the end, the numbers will be P minus 4, P minus 3, P minus 2, P minus 1. This set can be written like this. If you observe this set minutely, then you will see that the first and the last, their squares, P minus 1 square is congruent to 1 square modulo P. It's very clear. Why? Because if you open this square, then you will get P square minus 2P plus 1 and plus 1 on the other side will be cancelled. So is congruent to 0 modulo P, which is very, very clear, because P divides P square minus 2P. Similarly, the second last number, P minus 2 square, is congruent to the second number, 2 square modulo P. On the same lines, you can say, here you will get 4P. The rest will be the same. So, you can see now that the square of the first is congruent to the square of the last, the square of the second is congruent to the square of the second last and so on. So if I square these numbers, so I will not need to have all the numbers with me. I can leave the set here, because now the rest of the numbers are congruent to exactly one of the numbers in this set. And we know that a quadratic congruence has exactly two solutions. One is A, other is P minus A. So one solution will be here and the other solution will be in the set which I have removed. And now another thing to be observed is that x square is congruent to 1 square modulo P. This has a solution 1. This has a solution 1 in the set, because 1 square is congruent to 1 square modulo P. X square congruent to 2 square has a solution here, and so on up to P minus 1 by 2. You will have the solution of these congruent equations, and these numbers, when you compare with the set 1, 2, 3 up to p minus 1, then how many congruence equations are having solution now? Exactly p minus 1 by 2. And these p minus 1 by 2 equations which have a solution in the form of 1 square, 2 square, 3 square, or p minus 1 by 2 square, p minus 1 upon 2 whole square, those numbers will be the quadratic residues modulo p, and the rest of the numbers having no solution for x square congruent to a modulo p will be the quadratic non-residues. So this is a very straightforward theorem which says that in the set 1, 2, 3 up to p minus 1 there are exactly p minus 1 by 2 quadratic residues and exactly p minus 1 by 2 quadratic non-residues. Now let us have another theorem which will be helpful in finding those p minus 1 by 2 quadratic residues, what those p minus 1 by 2 quadratic residues are. From the earlier theorem we know that p minus 1 by 2 quadratic residues are there. From the next theorem we will get to know what those p minus 1 by 2 residues are. The theorem is, let GCD of A and P be 1, then A is a quadratic residue modulo P. Obviously P is an odd prime if and only if A raised to the power P minus 1 by 2 is congruent to 1 modulo P. So whenever your A raised to the power P minus 1 by 2 is congruent to 1 modulo P, A will be the quadratic residue, and if it is not, then it will be a quadratic non-residue. In the next theorem we will see that if A is a quadratic non-residue, then A raised to the power P minus 1 by 2 will be congruent to minus 1 instead of congruent to 1 modulo P. So there will be two things only. Either A raised to the power P minus 1 by 2 is congruent to 1, or A raised to the power P minus 1 by 2 is congruent to minus 1 modulo P. If it is congruent to 1 modulo P, then it is a quadratic residue, and if it is congruent to minus 1 modulo P, then it will be a quadratic non-residue. And exactly P minus 1 by 2 of those will give you congruent to 1 modulo P, and exactly P minus 1 by 2 will give you the result congruent to minus 1 modulo P. That means there will be exactly P minus 1 by 2 quadratic residues modulo P, and there will be exactly P minus 1 by 2 quadratic non-residues modulo P. But let us prove this theorem first. So for the proof, since we are having here if and only if, we will need the converse parts proof as well. So first I will prove it directly and then I will move on to the converse part. So let A be a quadratic residue of P. So then definitely there exists some natural number m such that m square is congruent to A modulo P, because A is a quadratic residue. So x square congruent to A modulo P must have a solution, and that solution I have taken as m. So m is a natural number which is the solution of the quadratic congruence x square is congruent to A modulo P. So m must satisfy that quadratic congruence, and that what I have done, I have satisfied that quadratic congruence by m. So m square is congruent to A modulo P. One thing is clear, that P does not divide A, because GCD of A and P is 1 and P is an odd prime, so P does not divide A, and if P does not divide A, definitely P does not divide m square. So this means P does not divide m square, and this means that P does not divide m. P does not divide m. Okay, P is an odd prime and P does not divide m means GCD of m and P is 1. And if GCD of m and P is 1, by Euler's Fermat theorem, we have m raised to the power phi p is congruent to 1 modulo P. You can write it as this m raised to the power phi p, you can write it as m square raised to the power phi p minus phi p by 2 is congruent to 1 modulo P. We are working with modulo P, and we know that m square is congruent to A modulo P, so this m square can be replaced by A. So replacing this m square by A, we get A raised to the power phi p by 2 is congruent to 1 modulo P. Now, what is phi p? For every prime p, phi p is equal to p minus 1. So this phi p is equal to p minus 1, and this gives a raised to the power p minus 1 by 2 is congruent to 1 modulo p, which we wanted to prove. So this is the direct part, and let us see now converse, how to prove the converse. That means if a raised to the power p minus 1 by 2 is congruent to 1 modulo p, then a is a quadratic residue modulo p. So let for the converse part, a raised to the power p minus 1 by 2 is congruent to 1 modulo p. Let g be a primitive root. Let g be a primitive root, then definitely there exists some number r, you can say, in the set of natural numbers such that g raised to the power r is congruent to a modulo p, because these are primitive roots, so this will be definitely satisfied. Now g raised to the power phi p, note that g raised to the power raise both sides to the power p minus 1 by 2. So gr power p minus 1 by 2 is congruent to a raised to the power p minus 1 by 2 modulo p. Now we are working with modulo p, and we know that this a raised to the power p minus 1 by 2 is given to be congruent to 1 modulo p. So this a raised to the power p minus 1 by 2 can be replaced by 1. So I am replacing this by 1. What I will get? I will get g raised to the power r into p minus 1 by 2 is congruent to 1 modulo p. And we know that if some number which is co-prime to p, its some power is congruent to 1 mod p, then this power must divide phi p by our Fermat theorem. So this r p minus 1 by 2 is divisible by phi p, because phi p is the smallest positive power which satisfies g raised to the power phi p is congruent to 1, and now g's power this is coming to be congruent to 1 modulo p, so phi p must divide this number. And what is phi p? Once again, p is a prime number, so phi p is p minus 1. P minus 1. So p minus 1 divides this number. So 2 times p minus 1 divides 2 times this number. So 2 will be cancelled here. So p minus 1 is common, so we can relieve p minus 1 from here as well. What you will get? 2 divides r. And 2 divides r means r can be written as 2 power times some natural number k. R can be written as 2 times some natural number k. Now consider this g power r is congruent to a modulo p, and substitute the value of r is equal to 2k here. So you will get g raised to the power 2k is congruent to a modulo p. Once again, this g power 2k can be written as g power k square is congruent to a modulo p. From here you can easily derive that x square congruent to a modulo p has a solution. This equation has a solution, and what the solution is? The solution is x is equal to g power k. So this quadratic equation, quadratic congruence, x square is congruent to a modulo p, is having a solution, and whenever this quadratic congruence has a solution, a becomes the quadratic residue of p. So a is a quadratic residue of p, as this quadratic congruence x square congruent to a modulo p has a solution in the form of g raised to the power k. So we have proved that if a is a quadratic residue modulo p, then a raised to the power p minus 1 by 2 is congruent to 1 modulo p, and vice versa. The converse part is also true. And now another theorem we are going to take. If it is very easy, or you can say it is just a corollary of the previous theorems. If GCD of a and p is 1, then either a raised to the power p minus 1 by 2 is congruent to 1 modulo p, or a raised to the power p minus 1 by 2 is congruent to minus 1 modulo p. Either this is true or this is true. And definitely we know that if this is true, then it is a quadratic residue modulo p. And since this theorem that a raised to the power p minus 1 by 2 is congruent to 1 modulo p gives that a is a quadratic residue is with if and only if, that means the converse is also true. If it is a quadratic residue, then it must be satisfied. It is if and only if. So what the condition left, that if a raised to the power p minus 1 by 2 is congruent to minus 1 modulo p, in that case your a will be a quadratic non-residue modulo p. So we are having, after proving this theorem, we will have a result. For example 11, you take the complete residue set 1, 2, 3, 4 up to 10. Take any number, suppose 5. You just check 5 raised to the power 11 minus 1 by 2. If it is congruent to 1 modulo p, then 5 is a quadratic residue of 11. If it is congruent to minus 1 modulo 11, then it is a quadratic non-residue modulo 11. So that we will do after solving this theorem. So what is the proof? Proof is very easy once again. We know that a raised to the power 5p is congruent to 1 modulo p because of Euler's-Fermat theorem. And this 5p is nothing but p minus 1. And we can write it as a raised to the power p minus 1 by 2 square. And once again we can take this 1 to the left hand side to make it minus 1 congruent to 0. And that means p divides a raised to the power p minus 1 by 2 minus 1, a raised to the power p minus 1 by 2 plus 1. And since p is a prime, if p divides ab, then p either divides a or divides b. So p divides this or p divides this. So from here you can derive that p divides a raised to the power p minus 1 by 2 minus 1, or p divides a raised to the power p minus 1 by 2 plus 1. From here you can say that a raised to the power p minus 1 by 2 is congruent to 1 modulo p, or from here you can say a raised to the power p minus 1 by 2 is congruent to minus 1 modulo p. In the first case, we have already proved that a is a quadratic residue, or else in the second case a will become a quadratic non-residue modulo p. So we have proved this theorem as well. And now one very general question to find all the quadratic residue of a prime or prime number. So as I have told you earlier, let me find all the quadratic residue and quadratic non-residues of 11. So the question is, find all quadratic residues and quadratic non-residues of 11. You start with this set 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. I am writing here the set of quadratic residues and the set of quadratic non-residues here. Let me check one by one and let us see what number goes in which set. This 1 raised to the power 10 minus 1 by 2 is congruent to what? Modulo 11. This is obviously 1. So it will be congruent to 1. No problem. So 1 is a quadratic residue and it will always be. And it will always be. 1 will always be a quadratic residue modulo any odd prime number. Let us see what about 2. 2. So 2 raised to the power 10 minus 1 by 2. That means, 11 minus 1 by 2, not 10 minus 1 by 2. So 2 raised to the power 5. 2 raised to the power 5 is further congruent to 32 modulo 11, and 32, when you divide it by 11 you will get 10. Congruent to 10 modulo 11 means minus 1 modulo 11. 2 raised to the power p minus 1 by 2 comes out to be minus, congruent to minus 1 modulo p. So minus 1 will give you that 2 is a quadratic non-residue. So your 2 will be here in this set. Now check out 3. So what happens if we take here 3? So 3 raised to the power 5 now. 3 raised to the power 5. To make it simpler, you can take it 27 into 9. 27 when you divide it by 11, the remainder obtained will be 5. So this 27 will be replaced by 5. And 5 into 9 is 45. 45 when you divide it by 11, the remainder obtained will be 1. So it is 1. And since 3 raised to the power p minus 1 by 2 comes out to be congruent to 1 modulo 11, this 3 is a quadratic residue. So 3 will go here in this set. So let us check what happens to 4. Let us see what happens to 4. Now we are having 4 raised to the power 5. Once again, to make the question simple, I am breaking it into the powers of 3 and 2. So 4 raised to the power 3 is 64 and 4 raised to the power 2 is 16. 64 when divided by 11 will give you the residue 9, and 16 when divided by 11 will give you the residue 5. Once again, 9 into 5 is 45 and 45 divided by 11 will give you the remainder 1. So it is again 1. So that means 4 is again a quadratic residue modulo 11. Let us see what happens to 5, the next number. So you will get here 5. Once again, the same process I will follow. I will break it into the two parts, 125 into 25. 125 divided by 11 will give you the remainder equal to 4, and 25 will give you the remainder 3, and 4 into 3 is 12. So 12 when divided by 11 once again will give you the remainder 1. So 5 is also a quadratic residue of 11. Let us move on to the next number, 6. What happens to 6? We know that there are exactly p minus 1 by 2 quadratic residues. That means 10 minus 1 by 2. That means 5. So exactly 5 quadratic residues must be there. How many we have obtained? 1, 2, 3, 4. One more will be here. And when we will obtain one more here, the rest of the numbers will be placed here. So let us see what happens to 6. So it is 6 raised to the power 5. The same process I am going to follow, breaking into two parts, 2, 16 and 36. 36 divided by 11 will give you the remainder 3, and 216 when divided by 11 will give you the remainder, this will give you remainder 7, I think. Yes, it will give you the remainder 7. 7 into 3 is 21. 21 will give you the remainder minus 1. So it is a quadratic non-residue. 6 will be here. Let us check the next number, 7. We will have to follow the process till we have 5 numbers here or 5 here. At any place you will get the 5 numbers, the rest of the numbers will be placed in the other set. So 7 raised to the power 5. You can break it into 49 into 49 into 7. 49 divided by 11 will give you the remainder 5. Once again 5, and 5 into 5 is 25. 25 divided by 11 will give you the remainder 3. 3 into 7 is 21, and 21 means minus 1. So 7 is also being placed in the second set, quadratic non-residues. Now we move on to the next number, that is 8. 8. So 8 raised to the power 5. Once again, breaking it into smaller parts, 64 into 64 into 8. 64 when divided by 11 will give you the remainder 9. Once again 9. 9 into 9 is 81. 81 divided by 11 will give you the remainder 4. So 4 here. 4 into 8, 32. And 32 divided by this, once again it will be minus 1. So 8 is once again here. So we will have to check the next number, 9. So this will be the last number, because if 9 is here, 10 will be here. If 9 is here, 10 will be here. Because each of these sets must have exactly 5 members. So 9 raised to the power 5. 9 raised to the power 5. Once again I am breaking it into the smaller parts, 81, 81, 9. So 81 divided by 11 will give you the remainder 4. This 81 once again will give you the remainder 4. 4 into 4 is 16, and 16 divided by 11 will give you the remainder 5. 5 into 9 is 45, and 45 divided by 11 will give you the remainder 1. So this once again coming out to be 1. So 9 raised to the power p minus 1 by 2 is congruent to 1 modulo 11 will give you that 9 is a quadratic residue. And now this set has p minus 1 by 2, 11 minus 1 by 2, 10 minus, that means 5 elements. So the last numbers 10 will be here, and now you can check that there are exactly 5 quadratic residues and exactly 5 quadratic non-residues. So with this question, I'm going to end this video. In the next video, we will have knowledge about Ligandre symbols and their properties. Till then, thank you. Thank you once again.